So it's a pleasure today to have at our colloquium Pravesh Kothari, and he will talk about sum of squares proofs, algorithms, and efficient algorithms and applications.
Yes, thank you, Hilbert and Camilo, for inviting me, and thank you all for showing up. Yeah, so I want to tell you about two highlights from this recent line of work that I've been very interested in over the past few years. My ulterior motive in giving this talk is because, at least, especially in the second part of the stuff that I will tell you, I think interest/help would be really great, because I think I'm out on a limb over there. So hopefully I'll get to it, and hopefully we'll have some conversations at least about something related. Good. So this talk is about sum of squares proofs, their connections to designing efficient algorithms for computational problems, and some recent rather surprising applications to making progress on problems in extremal combinatorics and coding theory by somehow analyzing these algorithms. And I want to get to somehow all three parts. So I'm going to begin with sum of squares proofs. So these are proofs. So there's got to be some theorem to prove, and the kind of theorem, kind of facts that I'm going to be interested in today are actually rather mundane. I'm going to be interested in proving multivariate polynomial inequalities. Okay, so imagine that you're given a polynomial in n real variables, and I'm interested in establishing that p is non-negative no matter what input I actually give to it. Okay, more generally, I could be interested in not just looking at non-negativity over all x in the input space, but perhaps I might be interested in looking at for all x that lie in some, let's say, variety. Okay, so for all x that satisfy some additional polynomial equations. Okay, in some sense, the most general setting here that I am interested in involves polynomial inequalities, or what people call semi-algebraic sets. But for today's talk, if you just think of varieties, it's perfectly okay. Good. So, I hope at this point all of you can think of at least one polynomial inequality, which is like some interesting theorem that you might know about. Let me tell you one of my favorite theorems. So here is a fact: sum ai square times sum ai square is bigger than sum ai times bi. Right? This is the Cauchy-Schwarz inequality. I think of it as a polynomial inequality in variables. Thank you. Right. So we all know that this inequality is true, at least with your help. And I view it as a polynomial inequality in variables a's and b's. It's a multivariate polynomial inequality. Good. So I'm going to be interested in not just any proofs. You may know many proofs of this inequality, but I'm interested in like very specific form of proofs today. I'm looking at something called sum of squares proofs. Okay. Here is a way to prove this inequality. I could prove a polynomial inequality by giving you some new polynomials, let's say s sub i's, and claim to you that p is in fact the sum of the squares of si. Okay. If I describe the si's to you and I claim this identity holds, then you can check for yourself rather easily that this got to be true, because you can just compare coefficients of every left and right. You can confirm that this identity holds, and once you confirm that this identity holds, you are convinced that p must be non-negative. Okay, we'll come back to the question of whether such a proof is even possible, but at least if such a proof was, if I gave you this si, then you are convinced that the inequality is true, and indeed it happens to be true in this case. That's the reason I wrote it. So it's like the more than 100 years old Lagrange identity that basically writes the difference as a sum of squares. Right? So you can explicitly write down the difference of the two sides as a sum of squares polynomials, and in particular it establishes that the Cauchy-Schwarz inequality must be true. Okay, good. But going back to this more general setting of variety,
I is less than j.
I actually think I might have the constant right, because there are two copies. Okay. Okay, coming back.
It's not if you sum over I and j, then everything will appear twice, but AI, okay, it is not. But I think you should. The way you wrote it, you get twice as much in the right side. Then.
Okay, I might be missing a factor too. I'll confirm.
Okay.
Yeah, sorry about that. But going back to this question of whether the more general setting of trying to prove polynomial inequality over a variety, there is a similar thing I could do. Instead of giving an identity of the form that P is a sum of squares polynomials, I in addition can allow you to shift by some polynomial combination of the input polynomials in the variety. And the rationale is that for any x that satisfies this constraints of the variety, this polynomial evaluates to 0. The sum of the squares obviously evaluates to something non-negative. So if such an identity were to be true, one, you can verify it easily, and two, it's a proof that P must be non-negative whenever x belongs to the variety. Okay, so I'm going to call this object sum of squares proof for today's talk. Okay, that's basically it. And so now we can wonder whether such proofs exist, and we are not the first ones, not by a long shot. This question of whether such proofs exist, was already being investigated like more than 120 years ago by Hilbert. And the motivation is rather simple, right? Like if you could really prove polynomial inequalities in this very simple, elegant way, it's somehow neat. You've got to find more applications, but by itself it seems rather neat. Okay. The bad news is that Hilbert already discovered that such proofs, at least for the unconstrained version, don't quite exist. And in fact, he had an inexplicit counterexample, and as of 1960s, we have very simple explicit counterexamples that show that there are non-negative polynomials over the real numbers, which do not admit a sum of squares decomposition. Okay, but nevertheless, it turns out that with the work beginning with Hilbert's 17th problem and lots of generalizations, there is effectively a version of the dream one might have had in 1800s, which happens to be true. Okay, so I'm going to tell you that now. So I'm basically stating some theorems, and let's see if I can pronounce it right. These are called Positivstellensatz theorems. And the version I'm stating is due to Putinar and Schmidgen from early 90s. They basically showed that if you make some additional assumptions about the variety, then in fact, a proof of non-negativity of this form always exists. Okay, so let me explain to you what this assumption is. So if W is the variety, so W is basically the set of x's that Qix equals 0. If W is something called explicitly bounded, and I'll describe it to you in a moment, then in fact P is non-negative if and only if it admits a sum of squares proof of the sort I just showed you. Okay. So what does explicitly bounded mean? I'll be a little bit vague about this. It means that the variety derives, and this is the vague part, it derives a constraint of the form some xi square is upper bounded by some number, okay, some finite number. Okay. And instead of trying to explain what this definition is, I'll give you two examples which are enough for this talk. So example one of explicitly bounded variety is the discrete hypercube, which I know to people who do algebraic geometry is super boring, but it's super interesting for me. It's like, I live my life on the discrete cube. Okay. So here is the discrete cube. Okay, xi square equals 1. Being satisfied by all of the n possible variables. The only solution is a finite variety. Only solutions are plus minus 1 to the n. Okay. So in particular, this variety, satisfies sum of xi square is exactly n. So it is an explicitly bounded variety. Another example that I would be interested in is the unit sphere in n dimensions, which is simply, a single polynomial equality, sum of xi squares equals 1. So for the purpose of this talk, you can simply, think of these two examples, and that's okay. Good. So for such explicitly bounded varieties, there is always a sum of squares proof. So in some sense, we've recovered, one possible version of Hilbert's dream, so to speak. Good. So, all right. So now, coming back, I'm going to look at these proofs, okay?
Now you didn't want to give us a definition of what these W's are, but
yeah.
How much more general is it really?
So, you basically just want that, sum of squares, polynomial combinations of QIs, should basically contain this polynomial.
Okay.
That's basically all. Yeah. So it's not, yeah. Good. All right, so, okay, good. So now let's think about like, these kind of proofs that we are looking at, okay? So far I've been like hand-waving my way around like easy to verify, but now I want to like, get into the formal details because, this is, if you've not noticed, it's a computer science talk. So we're going to be interested in like, complexity of things. So I'm going to ask in particular, how easy or hard is it to verify such a proof? Okay. So when I told you that if I give you this identity, you can check it. What does that mean? Well, if the right-hand side of this identity involves polynomials of degree at most some number d, right? And I'm working in the space of n variables, then each polynomial can be described by giving you, let's say, about n to the d different coefficients, right? And checking that the left-hand side and the right-hand side match is a matter of like checking n to the d linear equations holding true, right? One for each coefficient. So in some sense, the complexity of the proof, the amount of like effort you need to spend in order to check this proof, I'm going to ignore numerical precision issues, okay? They all work out when they, in some sense, we apply, but they're not automatic. For this purpose, for this talk, I'll ignore it, okay? But basically, you at least get a sense that, there's some n to the d as like some, amount of effort we'll have to spend in order to like, verify that this identity holds true, okay? So in general, this number d, the degree of the right-hand side, seems to control some measure of complexity of the proof. Okay, and I'm going to basically think of this as like some formal measure of how big or how complex the proof is. Okay.
Before you had weak inequality and then we have strict inequality.
Yeah.
Is there a reason for it?
Not really. I think, yeah, I was just being loose. So especially for our purposes, it won't make a difference because, we have freedom to shift the
When you
polynomial.
start approximating, then
Right.
it becomes an issue.
Exactly. So because I'm like shrugging the numerical issues under the rug, I don't have to worry about it. Okay. So, if the degree of the right-hand side is d, then, in some sense, the complexity of the proof is roughly n to the d. Okay. So the verification time, the time it would require to either describe this proof or for you to check it would be roughly like n to the d. Okay. The miracle, which in some sense happens to have a rather simple proof, but is really great, is that I'll get back to it. This is a great question, right? So in theory, I might, each SI requires n to the d different numbers to describe, but I don't know, I could have infinitely many SIs for all I care. And then, I don't really have a succinct description, but, it turns out that without the loss of generality, there are at most n to the d different SIs, okay? And I'll give you, some hand-wavy reason of why it's got to be true, okay? But before that, I want to mention that there is another miracle that happens. Not only, is this proof verifiable in n to the d time, whenever there is a proof of this size, there's basically an algorithm to also find it in roughly polynomial time in the size of the proof. So whenever such a proof exists, we can discover it in, time which is at most polynomial in the size of the proof itself. The proof may not exist, but if it does exist, then we can also find it, okay? So here is the, formal version of the theorem. The course is entirely because of numerical precision issues, okay? So, you have to be a little bit cognizant of what the coefficients on this proof look like if you have to state the correct theorem, but I won't do it for now, okay? So whenever, I have polynomials P and some variety described by polynomials QIs, a degree D SOS proof of non-negativity of P on the variety, if it exists, can be found in time, basically polynomial in the size of the proof itself. So this is great. In some sense, basically gives us an algorithmic engine, so to speak, to discover sum of squares proofs. And in some sense, this is the starting point, of the theory I want to talk about today, okay? So all these observations, by the way, are, on or before 2000, so everything is like at least 25 years old. I'm going to tell you, why this is related, because it gives you a very generic hammer for attacking optimization problems, okay? And I will explain to you by means of an example. Okay.
So here you don't assume explicitly bound.
I do. Sorry. Yes. Yeah. Everything I'm going to talk about today is for explicitly bounded varieties only. Good. So now, think of like discrete cube and the sphere. That's really, let's say, all we care about today. Okay. So I'll tell you how. You can think of, yeah.
So here, so for a general algebraic variety, you don't know the degrees of the polynomials SI a priori. So do you assume that you know that there is a proof where there are of degree D, or you just P's of degree D and the SI you don't say with the.
No. So first of all, the degree D is really of the right-hand side. It's not the degree of the P. It's the degree of the right-hand side. So what this theorem is really saying is that if there is a degree D sum of squares proof, meaning if there are SIs and phi's of degree at most D, then this algorithm will find it. Otherwise, it would say, well, I couldn't find it.
Okay.
Right? If it exists, it will find it. Otherwise, it will, give up.
Okay, and the explicitly bounded thing means that there is a theorem that in this case, for those kind of algebraic varieties, a non-negative polynomial function is sum of squares, but this would also give some theoretical bound for the degree of this polynomial.
Those are terrible. There are definitely explicit bounds known, but those are not going to be meaningful in any useful sense of algorithms. There would be way more than n, for example, the number of variables. They depend on other parameters, but at the very least, they're at least n. In fact, 2 to the n, the best known bound so far. Yeah. So but you should not even expect generic wins here, right? Like as I'll soon explain to you, there is no reason to expect that generically we'll do better here. We'll have to really look at specific problems in order to somehow derive any mileage out of this. Okay. So this example should make it clear. Okay. Good. So I'm going to tell you how this technology, this simple results like this actually are relevant to optimization. Okay. So here is an example. Suppose I want to optimize a quadratic polynomial. So this is just a simple quadratic, okay? So in general, all my polynomials will be low degree. So think of like degree 2, 3, 4, whatever, okay? So I'm trying to maximize a quadratic polynomial over the discrete hypercube, okay? This is, some hopefully like not so super boring problem. As I'll soon show you, it's actually a hard problem. But first let me tell you why with this, observation on the left-hand side, you can actually solve this problem, okay? So this problem is equivalent to minimizing over all bounds L, L minus Px has a sum of squares proof. Okay, so let me explain this translation first, okay? If the maximum of the polynomial P is at most some number, let's say opt, okay? Then what does it mean? It means that no matter what x I plug in, Px is never more than this number opt, which means that opt minus P is always non-negative, okay? So we know that if I have a non-negative polynomial on an explicitly bounded variety, then there's got to be a sum of squares proof. So all I'm saying is find me the smallest L such that L minus Px is non-negative, or equivalently, L minus Px admits a sum of squares proof of non-negativity. Those are equivalent, by the theorem on the left, or theorem on the, the leftmost board. Yes?
So we just want to find the maximum, not for which x it is of the. Excellent
question. So right now, I'm focusing on just trying to find out the maximum. Actually, there is a extension of this whole thing that succeeds in solving the search problem, but I will not define it for the purpose of this talk. So let's say our goal is simply to get an estimate of the maximum, the value of the maximum itself. We don't care about finding a x that achieves the maximum. Okay, good. So far this is good, right? And now, okay, so this is not helpful in terms of an algorithm because, the sum of squares proof could be of huge degree. So that doesn't help me, but at least it gives me an approach because I'll say, okay, I look for, some degree D sum of squares proofs. Now the problem is no longer equivalent, it's a relaxation, right? So I'm basically constructing upper bounds on the maximum, right? But as D increases, hopefully my estimates are getting better. So it at least gives me a generic hammer to attack discrete optimization problems like this. Okay, does it make sense? Now, one thing I want to point out that you should not expect this technology to succeed for all polynomials P for any reasonable constant degree D. The reason is that this problem is NP-hard. Okay, in fact, it's not just NP-hard to solve exactly, it's NP-hard to approximate. We know that there is some constant, so that we cannot hope, unless P equals NP, to find a constant approximation to its optimum.
Even for the quadratic case.
Even for the quadratic case. In fact, this problem is already sufficient to capture Unigame's conjecture. Okay, which
even just on the hypercube.
Even just on the hypercube. Literally, this problem here is already NP-hard to approximate up to some fixed constant factor. The constant factor is like, a subject of vigorous debate. It in fact is related and equivalent in some sense to the unique games conjecture, like what's the right constant. But we already know that, you can't do better than a constant factor approximation.
Which conjecture are you alluding to?
Unique games conjecture, it's like a conjecture in complexity theory, which I will not go into for the purpose of the talk today. Okay? But, the point is that you can still try to get some estimates. And it turns out that our best known algorithm, the best known estimate for, this problem, in fact, does turn out to be this technology. In particular, degree 2 is what is the best known algorithm. Like the best known algorithm simply corresponds to the degree 2 version. And we are in some sense in rather pathetic state of understanding of such problems because we don't even know if degree 4 improves the estimate in general. Okay, so we're already like, at an impasse, we are struggling with such problems. But I thought I'll give you an example to show you why even like a very, very special case of this whole world already captures, hard computational problems. So you should see like, there is no generic win to be had here. Even though, we have observations like this, they should not like somehow, solve all your problems for free or something. The hope is that you can use this as an engine to solve interesting problems, okay? And you have to do a lot of problem-specific work, but still it gives you a generic attack point for designing algorithms.
Is it any better on the sphere?
No. We also know NP-hardness results there. Our NP-hardness results are a little bit lacking there, to be honest, but we suspect that the same kind of hardness goes through. Like the difficulty seems to be like in terms of the reduction methodology rather than like algorithm design. But yeah, it's just as bad in some sense.
So why is it class NP? Because that is, you can give the answer, if some oracle give you the answer, that to verify it, it takes polynomial time.
Right, so that's why I said NP hard, but not NP complete. You can, so what NP hard means that if there was a way to solve this problem, then I would also be able to, decide satisfiability or like, solve every problem in NP.
He's not saying that problems in NP.
But he says that
If P equals NP, then there was.
Exactly.
So he doesn't say that, you don't say that it is an NP, but that if you solve it, then you get any NP.
Yeah, then P equals NP. So that's what means by, this problem in NP hard. This problem is not in NP by itself, but if you could solve it, then P would equal NP. Good, excellent, okay.
You know it is not in NP, or it's still a problem.
Well, the natural way of phrasing it is not in NP. There are ways to get around it, but yeah. Good, okay, excellent. All right, so, that's not what my talk is about. This was, the intro. So, the reason I wanted to give you this overview is because, it's, this is in some sense the world in which this technology was born.
This is much more than convex programming.
Excellent, yeah, so exactly the point I'm coming to now. So, this method over here relies on semi-definite programming. So this algorithm that, achieves this result here that allows you to find these proofs is based on semi-definite programming. In fact, I'll give you semi-definite programming. It's a generalization of linear programming, if you've heard about it, and, known to be strictly more powerful. I'll give you only like a one-line idea for why this is supposed to be true. I won't go into the details, even though the proof is simple, okay? The idea is the following. If I have, let's say I have a polynomial Q, let's say quadratic polynomial, homogeneous quadratic, and it is non-negative. Okay, meaning it's non-negative for all inputs X. Then this is if and only if Q is in fact a quadratic form of a positive semi-definite matrix. Okay, and this is a very easy observation, right? But it gives you a 1-1 correspondence between non-negative square, like quadratic polynomials and positive semi-definite matrices. This correspondence extends to even higher degree polynomials. So if this was degree 2d for some integer d, then instead of the quadratic form being on X, you take it to be on the vector of degree d monomials in X. Okay, and then the same correspondence continues to hold. What this means is that, if you are searching for a sum of squares polynomial, that equals, let's say, the identity over here, then that's equivalent to, finding, a matrix which is positive semi-definite and satisfies some linear equations. Okay, so this latter problem is called, semi-definite programming. It's an example of a convex programming relaxation. And it's one of those complex programming relaxations that happens to have an efficient algorithm. If these sentences did not make sense, it doesn't matter. This is the main observation, but I thought I'll make, just some comment about why this is supposed to be easy. Okay, good. So what I want to do next is tell you what has happened over the past 10 years. So initially, when people first thought of this observation and the usage in algorithm design, the hope was that we could solve problems like this a bit better. For better or for worse, that hope hasn't panned out as well as we thought. But something amazing has happened in the world of average case optimization, which is what I will now talk about. Okay, so what's average case optimization? Well, first you can think of it as a cop-out. Okay, we struggled, to solve problems in the worst case. When we intended to find algorithms that have good guarantees on each and every possible input, we are kind of struggling. We can neither do hardness or find efficient algorithms, right? So one reason you want to consider average case is because perhaps it will inspire new algorithms. Perhaps if you make assumptions on the instances, if they are not like worst case pathologies, then maybe you'll do better than worst case, okay? But, there is actually more, relevant motivation. It turns out that problems in some areas naturally come with input models. So for example, when you're trying to do statistics, the optimization problems that result often come up with instances which are generated from some probability distribution relevant to the problem. Similarly, like this is true in machine learning, statistical physics, and so on, okay? So for whatever it's worth, we're going to look at average case optimization problems like this. And I will tell you two examples or two highlights of what has happened over the past 10 years using this technology, okay? And this is just a glimpse. I'm very happy to chat more about any of these directions, okay? So first I want to talk about a problem in statistical estimation, okay? So let me tell you this problem and, describe why one might care about it. So in estimation problem, so here is a very simple example. Suppose I'm given n independently drawn samples from a Gaussian distribution with unknown mean and unknown covariance. Okay, and let's say I ask you to tell me what a good estimate for the mean and the covariance matrix of these points. These are all d-dimensional points. Think of d as large. Okay, then there's a very simple algorithm to solve this problem. I hope you all see it. If n is large enough, I can just average the points to get an estimate of the mean. I can just take the empirical covariance to get an estimate of the covariance. Okay, that's easy. Okay, so let's make it harder. We'll look at the problem of estimating a mixture of k Gaussians. So I don't have one, but I have k Gaussians, right? So there are k different pairs of means and covariance, so mean vectors and covariance matrices. All of them are unknown, right? I don't know mu i's or sigma i's. And I imagine that my data is generated IID from this mixture. What does it mean? It means that, about 1 in k fraction of the points are drawn independently from each of the component Gaussians.
But you know k.
Let's say I know k, yes. You can think of k as 2 for the purpose of this illustration, okay? So this, in some sense, for a very good reason, is literally in some sense the first non-trivial model studied in modern statistics. It's a very long history. In 1890s, Pearson studied some problem in biology, which is now considered to be the first paper in modern statistics, where he used a one-dimensional mixture of Gaussian model to somehow, figure out that there must be 2 different species in some data that he was looking at. It's like his first, data analysis or data science application, as people talk about it now. Okay, but of course, our problem is high dimensional and all now. So we are interested in still fitting this model, and there's more than a century of work on both applying this model in various fields and trying to figure out a good fitting algorithm. So what's the goal here? What's the optimization problem that turns out? Well, you're given input like this, right? And you have reasons to believe that your data looks like this. The reason might be that you have some heterogeneous data. Imagine data from multiple species or whatever. There's a natural source of clusters and data, and you want to figure out information about each cluster individually. Okay. The goal is to get estimates of these parameters. Okay, and of course, these estimates have to be closed in some relevant notion of distance. I won't write it down, but the distance in some sense, whatever is the most natural one, which is basically that, if I take the mixture on the estimated parameters, it should be close in variation distance to the true mixture. which is in some sense the right information theoretic notion of distance you could define here. Okay? But basically, like, at this point, you can just think of it as estimating the parameters in some right notion of distance. Okay. So this is called the mixture of Gaussians estimation problem.
Is K given?
Yeah, we'll assume that K is given. In fact, K is 2, let's say, for example, right? Like you can just think of the case of K is 2. It's already an interesting problem. Okay. Good. All right. So, there is a lot of work on this problem. And since the 90s, it was a, non-trivial project to figure out, whether there is a polynomial in dimension algorithm that can fit the parameters of an arbitrary mixture of K Gaussians. And it was resolved in, I'll write it down here, 2010 by Moitra and Valiant. Actually, Moitra was a postdoc here a long time ago. And so, yeah, that's one of his famous works. He basically figured out, they figured out like a polynomial time algorithm for fitting a mixture of K Gaussian, okay? Good, so, but what, already, actually, Pearson's original.
Berlin to the young Berlin.
It's one of the,
Worked on it.
it's one of the younger Valiants.
Okay, so he was here too.
This is Greg Valiant. Greg Valiant was here too?
We shouldn't forget that.
Okay, sorry, I didn't, somehow I mixed up my history. Excellent, okay. So, but this algorithm really assumes that the data is an IID sample from this mixture, okay? So it uses like the assumptions of the problem rather hard. It assumes that the clusters are Gaussians. It assumes that the data is really IID. And so, back in Pearson's original paper itself, this was like a non-trivial problem. Like, okay, we are making assumptions about model for the data. We are probably right in roughly right in choosing the model, but we can't quite assume that everything is exactly as we predict. Okay, so Pearson himself asked, we've got to have like some, algorithm that is a little bit, well behaved, even if the data is chosen from a model which is close to, but not quite our assumption. So Pearson wasn't very clear about this, but Kuki and Hilbert, Kuki was a professor here in the 60s. He actually began this project in a much more concrete way, and this project is now called robust statistics. So he asked this and other problems, in his concrete model where he said, we've got to somehow have an estimation algorithm that succeeds even if the input is chosen from a distribution which is close in variation distance to the true model. Okay, not exactly it, close in variation distance. So once, Moitra and Valiant figured out their algorithm, this became like the main open question in the area. This was asked like explicitly by a number of people. And, in some work that actually really, began as a postdoc here. So I was a postdoc at the time here. I actually gave a talk on some work like this a long time ago. Peter was in the talk too. This was like
Use the same notation, I assume.
Huh?
Better use the same notation.
Actually, I've forgotten if I'm using the same notation, but I would trust your memory. So it began here, and very recently. So the last paper has a lot of authors. So unfortunately, I'll be brief. So it's like with some students. So Bakshi, Diakonikolas, Gia, Kane, myself, and Vempala. This is a 22 paper. We found a robust algorithm. By robust, I mean that it actually also now works, even when the input is chosen from a model which is constant close to a mixture of K Gaussians. Now this looks rather weird. Like, why is it so much harder? It's hard for me to explain, I guess, in the space of this talk what's going on. What I can instead give you is like the new idea in this algorithm. Okay, instead of like trying to justify why this was interesting or hard or whatever, I'll just give you like the one key idea and how it relates to the sum of squares optimization like we've been building. Okay.
The variation distance you are alluding to at some point.
Right. The definition of variation distance.
Yes.
So if I have two PDFs, probability density functions, then the variation distance is up to a factor of half, simply the integral of the absolute value of the difference between them. So equivalently, it's basically like it's like saying what is the maximum difference in the probability assigned under the two different measures to any possible.
That's in one dimension. In higher dimensions, what kind of sets are you measuring the distance?
Good. So all possible measurable sets. All possible measurable sets.
All right.
So if I,
So take any measurable set, take any measurable function, right? Measurable bounded function, and take the difference in the expectations between the two measures.
Very strong.
and then you do it for all measurable
All, yeah, this is the max over all.
functions, or no, if you take the function is large, then you get more, and you have to
Max over all bounded measurable function.
bound it by one, let us say.
Bounded by one, let's say. Yeah.
Okay, so if you have a distribution which is on some discrete set, and then you move it a little bit, then the distance is very big because it's
Yeah. So it is very strong, and you're right. Like it might not make sense, for example, in discrete world, but we are in the continuous world here, right? Like we are looking at a mixture of K Gaussians.
okay.
Right? So at least here it is more justified. You're right. Like maybe we should be looking at some transportation distance or whatever when we're looking at discrete sets, but here it is measured.
No, right. You're doing the good thing, all sets.
Yes. Okay. So we found a robust algorithm, and I want to tell you, like, just one key idea, because I think, the idea somehow feels more appealing than the result itself, to me at least for this audience. Okay. So I'll tell you what the key idea here is. So any algorithm that achieves this result should be able to do the following task. Say I give you two possible distributions. One of them is simply the standard Gaussian distribution with zero mean and identity covariance. And the other is, let's say, mixture of two Gaussians. Right? Let's say uniform mixture. Right? And I could choose the parameters in whatever way. Now, if mu1, mu2, and sigma 1, sigma 2 are like not too close to each other, I should be able to tell apart these two distributions just by like, some small sample from them. If I can't even do that, then there is no hope for me to solve the problem of like learning measures of K Gaussians. Okay. So how would you do this? How would you solve the problem of distinguishing between a single Gaussian and a mixture of two? Well, you got to invent some property of Gaussians, and hope that that is somehow satisfied for the Gaussian distribution, but not for a mixture of two when the components are somewhat far.
That's what statistics is. You got to find a statistic. that
Yes.
distinguishes.
Yes. Yeah, it's all of statistics. So I guess I'm like step 0. Okay, so what property should we use? I'm actually going to use like a very natural property, which there's a long history of study in high dimensional probability. Some concentration property and some anti-concentration property. Okay, so let me describe what this property is. So if I look at any projection, so think of V as a unit vector. Think of X as the random variable. So it could be either, standard Gaussian or, this mixture. So X is a vector value random variable. So if I look at X drawn from N0 identity and take the projection of X on any direction, a unit vector, then, it has a tail bound, right? Like it's not going to be larger than T more than some e to the minus OT squared time. Right? This is a tail bound that holds for all Gaussians. This is equivalent to saying that, for every integer L, the 2L moment of X dot V, grows as order L to the L. Okay, so I'm asserting this. I'm not asking you to see this, but this is known to be equivalent. These two statements are basically up to some constant. They're equivalent to each other. So the moments don't grow too fast. That's what it is saying, right? Like the moments they're somewhat bounded. They don't grow more than like L to the L fast. Okay, so this is the concentration property. And apologies for my terrible board work, but I want to write now, maybe erase the result part here and write here.
Do it order L to the L or order L to the.
Yeah, so there is like some constant times. I can be a bit more specific. So CL to the L. Okay, good. So this is concentration, and one more property that Gaussians have is anti-concentration, which is that probability that XV is at most some small delta is at most order of delta. Okay, so this basically says that a Gaussian, when projected to any direction, cannot be too small too often, and this says that it cannot become too large too often. So it's like a concentration property and anti-concentration property. Of course, many more distributions than Gaussian satisfy this, but I want to be like more concrete and just list you this example. Okay, So now, I want to, okay, this is the property that we all know, and many people know for like 100 years or whatever, true for Gaussians, but we have to check that these properties hold from a small sample, right? And a priori, this is a problem because I'm trying to verify something about all directions. I have to show that if I have the samples x1 through xn, then there is no direction v in which, some small moment becomes too large, or no direction v where somehow, I am zero too often or small too often. So the problem that makes this computationally difficult is that, I'm trying to invent some measure, which will tell me what's happening in some very rare direction, which a priori is not clear at all. Okay, how might I find this direction? But here's the key idea. Okay, it turns out that, the property of being concentrated has a low degree sum of squares proof. Okay, so I'm gonna put it here, maybe right here for now. Here is a theorem. If n large enough, if number of samples is large enough, then, with high probability over the draw of the samples, okay, so on the right-hand side, I have the second moment, the empirical second moment to the L. On the left-hand side, I have the 2Lth moment, right? In general, this guy is tinier than this guy. But I'm saying that, this guy is not too much larger. It's larger by at most Ci to the L, which is a fact that holds in distribution. But now I view this as a polynomial inequality in variable V. It's a multivariate polynomial inequality. And the fact is that this polynomial inequality has a degree 2L sum of squares proof. Okay? So what does that mean? It means that, I can verify something about all directions V without actually going through all of them. I can indeed do it in time n to the 2L by the technology I showed you. Okay? So for Gaussians, actually, this turns out to be not so hard to see. It's, it's not difficult at all because, there's an equality here because we know Gaussian moments. But the great thing is that this actually succeeds, this kind of a technology succeeds not just for Gaussians, but for significantly more general distributions. So in this work with Steinhardt, we showed that exact same result holds true whenever the distribution satisfies an isoparametric inequality. So for example, the distribution satisfies a dimension-independent Poincare inequality. So I won't write down what this means. Some of you may have seen this before, but I'll give you examples. All strongly log concave measures, satisfy this Poincare inequality. In fact, if this so-called KLS conjecture is true, then all log concave distributions satisfy this property. In particular, you could take any convex body. The uniform distribution on this body, no matter what the body is, satisfies this property. And what this theorem is saying is that, for all such distributions, we can, efficiently check this concentration property in n to the 2L time.
What was KLS?
So KLS is a Kannan-Lovász-Simonovich conjecture. It basically, so it basically says that, that all log concave measures satisfy this, Poincare inequality with a dimension-free constant. It's, some statement about fast mixing of some natural Markov chain, okay, on convex bodies, but I won't go into it for this talk. Okay, good. So, right. So, so this is very helpful, because now I'm going to be somewhat hand wavy. The way you can use this observation is, you know that, if I gave you standard Gaussian, then such a proof would exist. But if I gave you a mixture, because it is not true, there is no proof of it and therefore no sum of squares proof of it. So I can just apply the technology and, at least solve this distinguishing problem. This is just supposed to convey to you why, there is some meaning in it. Of course, the engine requires some more effort, but that's the idea. There's a similar way to formalize anti-concentration inequalities. It takes a little bit more effort, but you can also, ask for a sum of squares proof of an appropriate formulation of this anti-concentration inequality. And it also turns out to have a sum of squares proof. And together, basically, these form, one out of maybe a couple important pieces in this new robust algorithm I talked about earlier. Okay, so
This is just a way of checking it. It's not Gaussian. Is that true?
yeah. So what I told you is just a way of checking it's not Gaussian, but you can also intuitively think of it as like finding interesting directions. Like, in some sense, this is saying, so an interesting direction will be
a set on which the discrepancy, which your variation is big.
Exactly. So, in some sense, if you can reduce it to a 1D problem, it's going to be easy intuitively. And so this kind of an engine allows you to find a direction where the action is, where, the distribution is markedly different from a standard Gaussian, and you can usually make progress there. So there is now, in fact, a black box theorem that takes such results and converts them into algorithms. It doesn't really go this way, but that's the intuition.
How big is L in this?
It's actually true for every L. The L you need to invoke for the robust algorithm is proportional to K. And it turns out that it's necessary. Okay, so D to the K is the kind of dependence you end up getting. It's known that this cost is necessary, so that's kind of the best thing possible. So when I mean polynomial time, it's for a fixed K. Think of like K is 2. Good, okay. So, by now, so I told you only one theorem, but there are lots of applications of such, proofs, like constructive proofs or like algorithmic proofs of concentration and anti-concentration. There's a whole theory of robust statistics that you can build based on like such, certificates. I just give you like one example of such a theorem, okay? So now, I'm going to switch gears and tell you about a second application, this time on, some discrete optimization problem, okay? Are there any questions in the meanwhile? Good, okay, let's do it. So what I want to talk about next is good old optimization on the discrete hypercube. Okay, gotta have one of them. I started with such a peon to discrete optimization. I gotta bring in hypercube again. So I'm going to look at 3-sat problem. So I don't know if you've seen this before, but in some sense it is. In a very precise sense, it's the first problem that complexity theorists study. Here is the problem, okay? So the input to this problem is a logical formula, okay? It looks like OR of 3 variables or their negation. So imagine that I have n truth variables. They are supposed to take values in 0 or 1, false or true, right? I have m clauses. Okay. Each clause is an OR of 3 literals. Literal just means variables or the negations. And I'm interested in finding the max fraction of constraints, max fraction of clauses that can be simultaneously satisfied. So if I run over all possible truth assignments to the underlying variables, and for each of them, measure the fraction of clauses they satisfy. Tell me the maximum possible. Tell me the best possible assignment. Okay. So this is the optimization version of satisfiability problem that you might have seen. The vanilla version basically asks, are the constraints all satisfiable? I'm asking something, step further. I'm asking, what's the max fraction satisfiable? The formula might be unsatisfiable, but I just care about what's the maximum possible fraction constraint satisfiable. Okay, very good. So, as you all hopefully know, this is this problem is NP-hard. So we, in general, do not expect a polynomial time algorithm for this problem. But I want to actually tell you a more fine-grained picture of this, because that will motivate the result I want to tell you.
So you just want the number, not to give the actual.
Yes.
It realizes the number.
Yes. So in general, like, of course, we care about the latter too, but, for this talk, I want to just stick to like, finding the optimum value for simplicity. Okay, good. So, what I want to now tell you is how the complexity of this problem changes as a function of the number of, clauses I have. So, back in like 30 years ago or something, complexity theorists had the intuition that if I have more and more constraints, the problem should get easier, okay? And what they did to prove this, so I'm going to write down, the number of constraints in log scale. So I'm writing the exponent of n. So think of like, constraints as n and square and cubed. So that's what I'm drawing here. And think of this as like the exponent of n on the running time. So log to the base n of the runtime. The runtime of the best known algorithm for the problem. Okay, so if I have n cubed constraints, when this number is 3, so like, constant times n cubed, which is like, basically constant fraction of all possible clauses are present, then there is in fact a polynomial time algorithm for this problem. And this is the result from early 90s. It's like, the first result that put this intuition into action, that dense instances are actually easy. Okay. It turns out that there is something slightly better that holds. If you go to density n square, then there is no polynomial time algorithm known, but there is a, non-trivial sub-exponential time algorithm known, meaning you can actually do better than 2 to the n. You can do something like 2 to the n to the 1 minus delta. Okay, so in this log scale, it looks like, sorry, bad drawing. So till, n square constraints, you basically need exponential time so far as we know. Once you hit n square, there is some, drop in this log scale, so you can beat brute force search. And then, once you have n cubed, you hit polynomial time. This is the best known picture. And in fact, it turns out that modulo some standard conjectures, not P versus NP, but slight strengthenings of it, this picture is known to be tight. So you can't expect it to be better unless, like, some conjectures that are widely believed hold true. Okay, good. So this is the picture of worst case 3-sat, and it's basically done and dusted in some sense. The story is very old. So what should we do? Well, just like I was giving you this spiel about average case optimization earlier, we should look at, like, maybe specialized instances and ask if these instances, which, somehow achieve this weird hard curve, are pathologies. Is there some real, concrete sense in which most instances are easy? So that's what people did. And what they asked is the question of smooth 3-sat. Okay, so I want to tell you this next. So this is a model proposed by Krivine in early 2000s, I think 2506. So what does this model do? So I start with a worst case formula. So basically an arbitrary 3-sat formula. And then I perturb each literal. So each, I go to each clause, I look at each variable that appears in the clause, and then I negate it, like I flip it with some small constant probability. Let's say probability 0.01, so 1 in 100. Okay, that's it. That's my model. Okay. So if I have, many more than n constraints, perhaps it's not a surprise that you should expect the resulting formula to be unsatisfiable with high probability. Like I have random flips going on. I have way more than, like, n constraints. So it becomes like the model becomes over constrained. So you should not expect, these formulas to be satisfiable. So the right question to ask is there a certificate of unsatisfiability? Is there some, easily checkable proof? We saw some examples of easily checkable proofs earlier. You could ask more generally, is an easily checkable proof that convinces me that such a smooth formula is unsatisfiable?
What does it mean, smooth formula?
Yeah, so smooth formula means you start from worst case and you perturb each literal, meaning you go to each clause, you take each variable that appears in the clause, and if it is negated, unnegated at 1 in 100 probability, and if it is negated, sorry, if it's not negated, negate it. If it's negated, unnegated, 1 in 100 probability.
Your certificate should work with high probability.
Exactly. So, I can't have a certificate that holds, for every formula. Otherwise, it becomes like basically the problem of, whether NP equals co-NP or the worst case 3-sat problem. So what I'm interested in is there a certificate that convinces me of unsatisfiability of such a formula with high probability over the smoothing noise? So, if you've seen this famous work of Spielman and Teng on smooth analysis of the simplex algorithm for linear programming, this model was inspired by that. So, Spielman and Teng in their famous work showed that, even though the simplex algorithm, which is like a very practical algorithm for linear programming, even though it's exponential in the worst case, if you just start with a linear programming input and perturb each, coefficient of each linear constraint, then it becomes, polynomial in expectation. This is the result, and this model was inspired right around the same time, and it was inspired by their work. Okay.
And how do you scale the noise with the size of the system? I mean,
So it's a fixed constant here.
It's fixed.
Yeah, fixed constant.
Okay.
So I'm a bit confused about this. There is a diagram is log n, which when it is 3, that is in other words, when you have approximately n cube so a positive fraction of all possible things. But what about the following? Suppose you divide the variables into classes, and so the interesting, let's say half of them are the interesting ones.
Yes.
So you have, and then you put, for the others, you just put something which is satisfiable. So then you will have a lot of things from the other. You see, you
Yes.
will have NQ because
So
of the
this is
other
the
half.
result about worst case.
But
This is the result about worst case.
The upper board is the worst case analysis. Now, the lower board, he hasn't said what he gets. Although he's going to tell us that he can tell with high probability. Otherwise, he'll disappoint.
Yeah.
no, but if you can solve. Okay, maybe I will tell.
Yeah, absolutely. Yeah. Okay, good. So yeah, so look at the smooth instance and you can ask, is this problem somehow much easier? Is there like a, much better algorithm that can convince you of the unsatisfiability of a smooth formula? So, even before smooth, you could consider random formulas. Like, just like literally construct a formula at random. Like every triple is random and the negation patterns are random. It's like a very special case of this smooth model. And so people, around 2017, they figured out the answer for this simple special case, the random case. And it turns out that the results do shift, okay? So it turns out that there is a polynomial time algorithm for such random formulas if the density is 1.5. If there are n to the 1.5 constraints, okay? So this line shifts over here. And the sub-exponential, this curve, it also shifts to basically just n. Okay, so it's like, the whole curve shifts a bit leftwards. Okay, the two densities shift from like n cubed and n squared to n to the 1.5 and n. So in some sense, the random instances are behaving in some simpler way than you might expect in the worst case. But the question is, what happens for smooth, okay? So it turns out that, first of all, these algorithms are captured by what I showed you, even though the way people proved it was not quite this. Turns out that you can import them and think of it as like, providing a sum of squares certificate. And it turns out that they are tight. So back in 2017, we showed that, these algorithms are tight even for random formulas. Okay. So what we did recently is showed, so this is joint work with Guruswamy and my student Peter Manohar. So we showed that the same curve for random actually is true even for smooth. So smooth formulas are literally as easy as random. They admit, so even though the certificates themselves, require more work, by the exact same bounds. Okay. So basically, like a minor perturbation makes a worst case formula as easy as random. Okay, good. So this is just a result about optimization. Camilo, can I take 5 minutes? I just want to tell you, the last part. I've told you the first 2 bullet points. It's a very hand-wavy version, but I'm going to tell you the last part of it. The applications part. So what have we done? We found an algorithm for, some smooth, perturbed, random perturbed 3-sat formulas. Okay, so now what might you do with it? So, so I teach a theory of computation class, and there is a class on 3-sat where I, tell them about this is like the biggest problem in the world. If you solve it, something great happens. And then I'm a little bit glib. I also tell them that, in principle, you can reduce deciding the truth of every mathematical conjecture to, basically just deciding the truth of the satisfiability of a formula. So if, you had an algorithm, you will succeed. So this is the only problem to study in the world. Of course, I'm being super glib there. But it turns out that this ability to analyze and in fact, have an algorithm that attacks these smooth formulas almost makes some of this spiel come to life, okay? So, over the past 4 years, what we've been able to do is take combinatorial problems, like questions about whether a certain combinatorial structure could exist, and convert the truth of such, claims into SAT formulas. It's not like the vanilla kind of construction you might think of. There is like some structure, like problem-dependent thing that you have to do. But it turns out by, the structure in the formulas, even though it's like a rather complicated one, it's rather not random, it still somehow fits the kind of techniques we have for analyzing the smooth formulas. So we can decide, in fact, we can prove that these formulas are unsatisfiable, the ones that result from a reduction from combinatorial problems, thereby basically making progress, at least resolving a couple of problems in extremal combinatorics, okay? So I want to give you one example of this problem, and that will be it, okay? And the example I chose is something that, you might hopefully enjoy. So it is actually a strengthening of Similarities theorem that, we all have heard about. So here is what, Similarity proved in the 70s. It's like, let's say, we're looking at 3 APs. So what he proved is that, there exists a delta strictly less than 1, right? Such that for all subsets X of, the first n natural numbers, as long as X has at least delta n elements, X contains a 3AP. A 3-term arithmetic progression.
I think 3-term was known before.
Actually, yeah, this is Roth's theorem. Somebody proved it for like, arbitrary fixed KAPs, okay? But let's say,
The reason I say that, I want to see your application, whether it's for just 3.
Yes, yeah. Good. So now what? So, back in the 80s, I think maybe Bourgain was the first who asked this question. He asked, okay, suppose, so this is saying that every dense set contains a 3AP. But now I want not just a 3AP, I want a 3AP from one of a small number of possible allowed common differences. Okay. So here is, a strengthening. Okay. Choose D subset of first n natural numbers. These are like the set of allowed common differences at random. So random set of size some parameter n. So I'm going to first choose a D to be just a m size random set and ask the same question. What is the smallest n such that every dense set contains a 3AP, but not just any 3AP, a 3AP where the common difference comes from this D. Okay, so it's like, some kind of a sampling theorem that, these small set of random common differences suffice for basically every dense set containing a 3AP. Okay. So, Bourgain actually proved it for different sets, which is like 2 APs. He basically proved that, if you take a random set of size log capital N.
For 3. You did it for 3, right?
No, for 2, just different sets.
No, different sets, but he's still working with 3 APs. 3-term progression.
So I think he just proved that, every dense set, there is a pair whose difference would lie in this.
Yes, what I'm trying to say is he's using Roth's method. He's using harmonic analysis method.
Yes, he's using harmonic analysis for sure. Yes. Eventually, there is also a proof of this theorem using alone Reitman, like, this expanders, with random generators on any group. But, there's a similar question for like 3 APs and, 4 APs in general. You can ask, what is the smallest set of, random common differences that suffice for Similarities, theorem to be true, okay? So one thing, so this is, this is not, by result we proved last year with Omar Al-Rabi'a and all the authors over there, plus a connection that appeared in a paper of Priet, Gopi, and Duer from 16, implies that m less equals n to the 1/3 suffices. I think the conjecture here is like log capital N holds even for 3 APs. Till 2023, the best bound was capital N to the 1/2. But, out of this machine of like taking a combinatorial problem and making a SAT formula and then like, refuting that formula, like finding a proof of unsatisfiability of the formula, you can actually make this estimate go to n to the 1/3. So there are like a few applications, but I thought, this might be the one that requires least background. So I'll just leave you with it. Solved.
This is for arithmetic progression of size 3 with difference m.
Yes, but difference from a random set of D. So basically the theorem says that if you choose a set capital D of size small m uniformly at random from the first n integers, then with high probability over the choice of D, every dense set contains a 3AP with a common difference from D.
Okay, so you at least proving Roth's theorem.
Yes.
So what method you use?
Sorry. So we are not proving Roth's theorem. We actually start with Roth. We have to assume Roth to prove this. So it doesn't recover a new proof of Roth. It's a sampling result, right? Like if you start with Roth.
From.
Right. So, you start with the density version of similarity, like Roth, like you're not just one AP, but like lots of 3 APs. And then you show that, most of them must be preserved even when I sample.
Okay.
But M should be, I mean, do you say that M is around n to the 1/3, then this is with high probability.
Yeah, so
If M is too small, it's not.
Right. So, you're choosing a D to be a random set of size M, and the claim is that some M less than n to the 1/3 suffices.
Some M. Okay.
Yes. Yeah. Sorry, I was not like super clear there.
Okay, and then the larger ones will also suffice.
Yeah, of course.
Okay.
So the conjecture there is that, logarithmic size sets suffice, but, we don't know how to prove. We are very, very far from proving it.
Can you go beyond 3?
Great question. So, a paper like a few months after we did this work is due to Castro, Silva, and Riet. Doing it all in the wrong order. Also 23. They basically extended this result to, KAPs, and the bound changes. It's really capital N to the 1 minus 2 over K. Okay, so it gets worse as K grows, even though like the answer we suspect is log capital N, for any fixed K. The bound, like the current techniques, the bounds get worse.
Okay. For large K, okay.
So it's less interesting if you look at the bounds for large K.
Any more questions?
What kind of problems do you expect this like 3-step technique to work for? Is there any like intuition you can say?
Yeah, like it is coming from like problems which naturally have some local constraints. So, I did not describe the machine at all, but the formulas that we construct come from combinatorial objects satisfying some constraints. So like, when your combinatorial object has the property that it satisfies some constraints which are naturally written as like local, like, things that look at triples at a time or 4 tuples at a time, then, at least a priori, you could try to think about this method. So it turns out that, there is a way to translate this sampling problem of 3 APs into like, some triple constraints. And so that's the reason why it works here. But yeah, that's nice. So, basically problems which have to do with, some low identity hypergraph type constraints.
Could you prove circuit lower bounds with this? Like to rule out a 10n size Boolean circuit for some function.
As
this locale.
Yeah, but I don't know. I haven't. Yeah, I guess I don't understand anything. Maybe it's an interesting thing to try, but yeah, I definitely haven't tried. It's a good question. Yeah.
Okay, if there are no more questions, thank you.